parts, because everything is interlinked. If you look closely enough at any local part, it should tell you about the distant parts. So we used in the old days to talk about this in a kind of half-joking but actually quite serious way. One should be able to deduce the expansion of the universe and even the approximate value of the Hubble constant from the existence of bus tickets. You might like to think about that. It's actually rather nice. But the point is, distant regions have an important influence on local physics, and that's what I want to talk about in this talk. So the first theme is the uniqueness of the universe, is the unity of the universe, and the second theme, which I've already mentioned, is the uniqueness of the universe. And again, from Dr. Sharma, with only one universe available for study, we have no basis for distinguishing between its fundamental and its accidental features. The idea that certain features of the universe are accidental is a somewhat disturbing one. It is possible they would not appear accidental in a more comprehensive theory of the universe. And the point about this in the study of cosmology is that when you look at the universe per se, it is not easy to distinguish between physical laws and boundary conditions. This is the point I want to return to. When you're dealing with local physics, it's easy to say what is a boundary condition and what is a physical law. But when you're dealing with cosmology as a whole, this distinction is not an easy one. What we experience as an inviolable physical law may in fact be the consequence of particular boundary conditions for the universe as a whole. And the point about it is we can't test these features. We are given the boundary conditions for the universe, and so we can't rerun the universe or compare it with any other physically existing universe. And this is why it's actually difficult to distinguish, in the case of cosmology, between initial conditions and boundary conditions. Now, a framework which will at first be a little bit unusual perhaps, I want to distinguish between bottom-up and top-down interactions. And the way we normally think about this, the way we're kind of trained as physicists, is to think of bottom-up interactions where local physics determines what happens in the universe as a whole. But actually, a lot of what is going on in the universe goes the other way. The universe as a whole has a strong interaction with local physics. And these kinds of top-down interactions, which are indicated in this occur and are important in the real universe. They're not emphasized in usual physics discussions because the usual idea in physics is to talk about an isolated system. Now, there is no isolated system in the real physical universe. And this physical discussion, this idea of the isolated system, is an idealization, and it cannot actually be realized in reality. And this comes back again, a similar kind of quote about this isolation. We can only hope to understand any part of the universe by taking account of the whole. That's another way of saying that there are no isolated systems in the real physical universe. Now, let's look at some bottom-up interactions. Now, this is where local physical laws, for instance, the Einstein field equations, determine the large-scale structure of the cosmos. For instance, the Friedmann equation, which I wrote down before. And what you have is a local matter density rho there, and that local matter density then determines the space-time curvature and the rate of expansion of the universe. And we've looked at that in some detail. What this means is, in order for the temperature for the hot Big Bang era, for instance, in order to understand the expansion of the universe, you must know the local physical structure. You must know that the density of the matter consists of neutrinos and antineutrinos and mu neutrinos, anti-neutrinos and photons. During this time, that gives you AT to the fourth plus 7/4, AT to the fourth from the neutrinos and the photons, which is related to the temperature. In this way, you put this into the Friedmann equation, and from the Friedmann equation, you get the time in relation to temperature, or the temperature in relation to time, during the hot Big Bang epoch, and this is what determines the results of the nucleosynthesis calculations. This is bottom-up interaction, all of these small little particles ganging together to tell the universe at what rate it should expand, and therefore the rate at which the temperature of the universe decays. It is also because of the behavior of these local particles, you get the initial singularity in the universe through the Ray-Chardy equation, which I discussed with you before. Within a finite time ago, there is a singularity. Now, this is because of all these local particles adding up their gravitational attractions. That's bottom-up interaction in the universe, resulting in this extremely dramatic effect, at least according to the classical theory, of a singularity at the beginning of the universe. And so, bottom-up effects in cosmology, this is what a lot of cosmology is about. It's really very dramatic. And to put this more generally, what you've got in the bottom-up interaction, you've got quantum gravity underlying particle physics, underlying nuclear physics, underlying atomic physics, underlying statistical mechanics, kinetic theory, classical gravity, the fluid picture, the universe, and basically you've got bottom-up interaction